Hello everyone, my name is Nandita Goyal. I am working as Assistant Professor in Department of Information Technology at ABES Engineering College. Today I am going to discuss the topic some general identities which apply on sets. So, in today's lecture we will be discussing various laws which can be applied on sets. The first one is going to be idempotent law, associative laws, then we will be discussing commutative laws, distributive laws, identity laws, involution laws, complement laws, and at last we will be discussing De Morgan's laws. So starting with the first law, that is idempotent law, all these laws can be applied on sets while performing the operations like union, intersection and complement, and all the sets satisfy these laws. The first law, idempotent law, what it says that if we take union of any set with the set itself, it will give me the same set. For example, if I have a set A with me and I take the union of that set with the same set A, I will again get set A. So this is the Venn diagram which shows the region which I will be getting after applying this law. So first I will select set A. The entire set has been selected and it is shown by the shaded area. Union of set A with set A again gives me the same area, that is set A itself. Now this same law can be applied for intersection as well. Now I again have set A and I apply intersection operation of that set on the same set. I will again get the set itself. So again in this diagram the shaded area shows the set A which will be selected as a result of A intersection A. So this is the first law which is known as idempotent law. Now coming to the second law which is known as associative law. In the first section we have discussed the associative law for the union operation. So what does it say? It says that when we apply the union operation on any two sets A and B and then we take its union with the third set C, its resultant will be same as if I take the union of B and C first and then union with set A. So in order to verify this law, I have used this Venn diagram. So for left hand side, first we have taken three sets A, B and C. Then we have shown the union of A and B with red and green color. So this gives me A union B. Now when I take the union of this resultant with set C, then I have used this blue pen to show the union with set C. So the entire region which is shown on the left hand side is the set A, B and C, entire region of these three sets. On the right hand side, I have again tried to verify the right hand side of the law for union operation. So again, when I draw the Venn diagram and apply union operation on B and C, we will get this region which is shaded with horizontal lines. Then while I apply union operation on set A, I have used the vertical lines. So the entire region which is being depicted by this diagram is the entire region of set A, B and C. So we can see that the left hand side diagram is similar to the right hand side diagram. So associative law holds for union operation in sets. Now associative law has been verified for the intersection operation. So what does it say? It says that if I have two sets A and B and I apply intersection operation and then I take its intersection with the third set C, it will be same when I take the operations as B intersection C and then its intersection with A. Again, we have verified it using the Venn diagram. So we have drawn the Venn diagram showing the sets A, B and C. So A intersection B is the region which is shown by the horizontal lines. Then when we take its intersection with set C, so only the common region comes in A intersection B intersection C. So this region is shown by this pink color. Now coming to the right hand side, again we have drawn the Venn diagram showing sets A, B and C, and the area depicted over here is again the same region, that is the central part which is shown by the pink color, and so we can say that the left hand side is again equal to the right hand side. So the associative associative law even holds for the intersection operation when we apply it on sets. Now coming to the third law. The third law is known as commutative law. So what does the commutative law says? Commutative law says that if I take A union B, that is A and B are two sets, and I apply A union B, so the result will be same as when I apply B union A. So this thing has been again verified by the Venn diagram. So left hand side shows you A union B and right hand side shows you B union A. So we perform the union operation in any order, we will get the same result. Now coming to the same commutative law for intersection, it again says that if we take A intersection B, it is very similar to B intersection A. For this again we have drawn these Venn diagrams and the region is being shown. So A intersection B is shown by the pink color, and when on the other hand side we draw the Venn diagram for B intersection A, so the common region is again the central one, which is shown by the pink color. So left hand side is again equal to right hand side. So we can say that commutative law holds for intersection as well as union operation for sets. Now coming to the next law, which is known as distributive law. So the distributive law here, we'll first see the first part, that is A union B intersection C. This is equal to A union B intersection A union C. So we have distributed union operation over here. So we have opened the braces and we have distributed this union. So it becomes A union B intersection A union C. Now we have to verify that is this law applicable for sets. So we have drawn the Venn diagrams. So the Venn diagram contains three sets A, B and C. We have shown the region. First we find out the region for B intersection C. This is the region which has been shaded this way. Then for A union B intersection C, we have included the set A with this region. So this is the region which is shown on the left hand side. Now again when we talk about A union B and A union C and then its intersection. So first we'll find out A union B. So A union B is shown by the horizontal lines. Then A union C, that is shown by these diagonal lines, and then intersection of these two, the region where both the lines are present, that is again same as the one in left hand side, which is this central region. So we can say that the left hand side is again equal to right hand side and the law holds. Now here on the right hand side we have shown the same law for intersection operation. So for intersection it will work as A intersection B union C. Here the intersection operation can be distributed. It will become A intersection B union A intersection C. So both the sides should again be equal. So here we have again verified using the Venn diagram. We have shown the regions which are represented by the left hand side, that is this portion which is shown as flat. Okay. So this shows you A intersection B union C, and on the right hand side we have again shown the region A intersection B, that is the central part A intersection C, and then we have taken the union. So left hand side is again equal to right hand side. Now next we have identity laws. The first identity law says that if I take any set A and take its union with a phi set. A phi set is basically a null set. So what I will get? If I unite any set with a null set, I will get the same set itself. So A union phi will again give me A. If I take the intersection of any set A with a universal set. So a universal set is one which contains all the elements. So the intersection of these two will obviously give me the set A itself. Next we have, if I take a set A and its union with universal set, I will get a bigger set, that is the universal set. And the last one is, if I take A intersection phi, that is null set. So what I will get? Null set contains nothing, so I will get the set phi itself. So these are the identity laws. Now next, coming to the next law, which is known as involution law. So what does the involution law says? It says if I have a set A and I I take the complement of set A and again I take its complement, I will get the set A itself. So to show this with the Venn diagram, I have taken this set A. Okay, so first of all I will take the complement of this set A. So the complement of this set A has been shown by these dots, that is A's complement. Now if I take the complement of this portion again, so what I'll get this inner portion which is shown by the vertical line, that is the set A itself. So we can say that the involution law holds. Now coming to the complement law, the first part of the complement law says that if I take a set A and I take its complement and then I take the union of these two, that is A union A's complement, I'll get the universal set because it will contain everything, A as well as A's complement. So that means it is going to depict universal set. Now if I take A and its intersection with its A complement, now I take the set A and everything which is outside A and then I try to find out the intersection of the two. Obviously I am not going to get anything, that is I will get null set as the resultant. Now next is if I want to take the complement of the universal set. Universal set is one which contains everything. So whenever I take the complement of universal set, I will get nothing. So I will get a null set, that is phi. Now if I want to take the complement of a null set, that is phi set. So complement of null set will give me universal set. So all these laws come under complement laws. Now coming to the last law, which is known as De Morgan's law. So what does the De Morgan's law says? That if I have two sets A and B and I take the union of these two sets and then the complement, so the resultant will be equal to A complement intersection B's complement. That is when we open the braces, we'll just reverse the sign. In place of union, we'll make it as intersection. So to verify these laws, we have again used these two Venn diagrams. The first one shows you the left hand side and the second one shows you the right hand side. So what is the area which is depicted? If I take the union of these two sets, then I get this horizontal lines area. Okay, when I take the complement, I will get the area outside. When I talk about the right hand side, that is A's complement. A's complement will be everything if I leave the set A, and B's complement will give me everything if I leave the set B. So what will be the intersection of these two? The outside area. So this shows you A's complement intersection B's complement. So this area and this area depict the same thing. So we can say that De Morgan's law holds for union operation. Now we have shown on the right hand side the De Morgan's law for intersection operation. So when I apply intersection A intersection B's complement, what I will get when I open these braces, A complement, the sign will reverse, that is it becomes union B complement. So again, to show that left hand side and right hand side are same, we have used the Venn diagrams. So first of all, we will take A intersection B. So this is the area which has been depicted in red. So its complement will give me everything outside this area. Just leave this area. And similarly, if I want to find out A's complement and B's complement, A's complement is everything other than A. B's complement take everything other than B. And the union of these two will give me everything other than this central part, that is A intersection B. So these two areas are again the same. So we can say that the intersection operation also holds for, the De Morgan's law also holds for the intersection operation in sets. So this was all from my side for today. Thank you.